So hello everyone. I am Edmund Dervakos. I'm here to present our work concerning genre recognition from symbolic music with convolutional neural networks. Okay, so our motivation for this work was twofold. On the one hand, automatically recognizing genres is a very useful tool for organizing and tagging large collections of music, which in recent years have grown to contain hundreds of thousands of songs. Genre recognition is also an inherently difficult problem to solve in the symbolic domain, since there usually isn't a clear definition for a genre, and the ground truth labels cannot be considered reliable. However, this motivates us to explore ways in which we can solve this difficult problem. So, genre recognition in the symbolic music domain of MIDI files and scores is even harder than it is in the audio domain, since symbolic music does not fully capture information which might be important for solving the task. For instance, the different sounds of various instruments or nuanced aspects of human performance. It is also among those tasks which has not yet been dominated by deep learning-based approaches, as has happened in other domains. There are, however, successful applications of deep learning-based methods in the literature, which get good results. However, to our knowledge, none achieve good enough performance to be practical. Symbolic music representations such as music XML, MIDI, or even text are emerging as an important data domain, since these technologies are being widely used commercially and creatively. As a result, we consider symbolic music to be an important domain for artificial intelligence, especially concerning algorithmic composition and accompaniment and continuation of music. Finally, exploring new approaches for solving a task, such as genre recognition for symbolic music, may benefit other tasks of the domain, such as style and mood classification, in addition to potentially being useful for other domains where data is structured similarly, such as natural language processing. Some recent approaches for genre recognition from symbolic representations of music, which are among those which achieve the best results for large-scale datasets, are mainly based on pattern recognition or inspired by natural language processing. Ferrara and Lemstrom, for instance, use pattern recognition algorithms SIA and P2 in order to extract patterns from a large corpus of MIDI files, and then use these patterns in conjunction with a simple logistic regression classifier in order to predict a song's genre. A benefit of this approach is that the collection of patterns which they have extracted from MIDI files is openly available and could be useful for musicological research. Another common successful approach for solving the task is to utilize sophisticated algorithms from natural language processing. An example is the application of hierarchical attention networks on text representations of music proposed by Dugirala and Mo. Another example is PIRDI, proposed by Liang et al., which consists of 4 word embedding models defined on 3 vocabularies: chroma, velocity, and note state. These models are applied in different music information retrieval tasks, among which is genre classification. The mentioned related work is a primary motivator for attempting to solve the task with one-dimensional convolutional neural networks. CNNs have been widely successful in other domains, such as computer vision, raw audio, spectral representations, and more. 1D convolutional neural networks in particular have been applied in a variety of tasks, and in some cases have emerged as an efficient replacement for recurrent neural networks. An example are DeepMind's WaveNets, which are 1D CNNs for generation of raw audio, and applications in other domains, such as genomics, with models such as Basset. The inner workings of a 1D CNN can be argued to include pattern recognition. If a convolutional kernel represents a pattern, once it activates, it has detected the existence of the pattern. In addition, a CNN increases in depth. As the CNN increases in depth, its operation is close to hierarchical feature extraction, where lower level features are extracted from earlier layers and higher level features from deeper layers of the network. These notions seem to be closely linked with existing approaches for genre recognition from symbolic music, such as the one presented in the previous slide, which motivates us to explore the use of 1D CNNs for solving this task. So in order to design an efficient and effective 1D CNN for genre recognition, we focus on the notions of receptive field, depth, and width of the network, given the limiting factor for available computational resources, the number of trainable parameters. The receptive field of a network refers to the size of the network input on which the particular layer depends on. For instance, if the first layer of a network had kernels of size 3, then the layer would have a receptive field of 3. Efficiently increasing a network's receptive field is crucial for effectively capturing features across multiple timescales. By stacking convolutional layers, receptive field increases linearly with network depth and with kernel size. However, simply increasing depth increases the number of trainable parameters and could give rise to difficulties during training. So there are various techniques which are used for increasing the receptive field more efficiently. These include using dilated convolutions, using strided convolutions, or the most common approach, using pooling layers. Finally, closely linked with the receptive field is the depth of the network and the width of each layer's kernels. One can get the same receptive field and number of trainable parameters for a one-layer network as with a multi-layer network. So we believe that it is worth exploring different configurations for finding the most efficient and effective configuration of layers. So 1D CNNs accept at their input two-dimensional data, where the first dimension represents length and the second represents channels or features. They are similar to 2D CNNs if they acted on an image with a height of 1 pixel. So in order to convert MIDI files into a suitable representation, we first convert them into multitrack piano rolls by using the Python library PyPianoRoll. A multitrack piano roll is a set of single-track piano rolls. A single-track piano roll is a 2D array where each column represents a different time step and each row represents a different MIDI pitch. The value of a cell in a single-track piano roll represents the velocity of a specific pitch at a specific time step. So having converted the MIDI files into multi-track piano rolls, we then perform an element-wise sum of the constituent single-track piano rolls, and we normalize them, leading to a 2D array equivalent to a sequence of vectors which is suitable to be fed to a 1D CNN. So besides experimenting with straightforward architectures of 1D CNNs, we also proposed our own architecture, which acts on multiple versions of a piano roll, each at a different resolution. In the general case, a piano roll can be organized hierarchically into a tree. Trees are an effective representation of symbolic music, since they are able to capture information, patterns, and structures at multiple different timescales. There are, however, many different ways of constructing such trees from a piece of music, in addition to different approaches for feeding tree representations to neural networks. So in this work, we focus on a simpler version of this approach, where each level of the tree represents the original piano roll, but at a lower resolution. Then our architecture, MuSeReNet, which stands for multiple sequence resolution, accepts at its input all levels of the tree and utilizes them in order to predict the genres which characterize the original MIDI file. Okay, so specifically in our implementation, given a cumulative piano roll, which is a sequence of pitch vectors, we feed it serially through a series of average pooling layers, each of which effectively reduces the resolution by a factor of 2. Each output of an average pooling layer represents a level of a tree from our general framework. We then treat all levels of the tree as different inputs to the neural network, which are fed at different depths of the network. The intuition behind this approach is as follows. One feature which could intuitively be useful for genre recognition would be the key signature of a song and the scale used. The simplest way to extract such a feature would be to look at the frequency of appearance of each individual note across the whole piano roll, which in our case is represented at the root of the tree, the lowest resolution, essentially a sequence of length 1. The leaves of this tree are the original piano roll, which is obviously useful for the task since it contains the most fine-grained information available. All levels in between attempt to capture information at different timescales. for instance, levels closer to the leaves, might be able to capture information concerning the harmonic progression of the music. While moving towards the root, we are able to represent lower grain information, such as sections, modulations, and more. The way we handle all the different resolution inputs within our architecture is as follows. The original sequence, the leaves of the tree, are fed to a block which consists of a stack of convolutional layers, followed by a pooling layer. The output of this block will be a sequence of half the resolution of the original sequence. Then, to this sequence, we concatenate along the final axis the original sequence at half the resolution, which is also half the length of the original sequence, effectively enriching the output of the previous convolutional block. We repeat this process log sequence length times until we reach the root of the tree. This final length 1 sequence is fed through a fully connected layer with sigmoid activations, each neuron of which represents a specific genre, which is the desired output. So, to evaluate this approach for genre recognition on a large scale, we set up the following experiment. We implemented a set of neural networks consisting of stacked convolutional blocks and compared the performance when using multiple sequence resolutions at the output of each block and when using a standard architecture where the original sequence is fed at the first layer of the network and there are no other inputs. With regard to the convolutional blocks themselves, we experimented with a deep block consisting of 3 stacked convolutional layers and a shallow block consisting of only 1. We also experimented with different lengths of input sequences for which we assigned as values powers of 2, ranging from 64 time steps to 2048. As evaluation datasets, we experimented on the commonly used subsets of the LAC MIDI dataset, namely MASD and topMAGD, in which each piece of music is annotated with multiple genre labels. We compare our results with other works which have been evaluated on the same datasets. Finally, for evaluation metrics, we compute precision, recall, micro and macro F1 for each configuration of the experiments. We have more details about the experimental configuration in the full text of our paper, including a GitHub repository with code to run the experiments. So the aforementioned deep block and shallow block were designed in such a way that they have the same receptive field, same number of trainable parameters, and have the same input and output shapes. We chose a kernel size of 24 for the shallow block, since the initial piano rolls are at a resolution per quarter. I think we had a disconnection.
Yeah, I feel that.
Yes, we are resuming at the same slide. Okay, so here we show the sizes of each of the 2 datasets we used, in addition to their label distribution. So both datasets suffer from extreme imbalances, which are to an extent representative of the imbalances seen in the real world. So for this work, we chose not to use any techniques for handling these imbalances, such as undersampling of common labels or oversampling of the rare ones, since we are interested in seeing how different configurations perform under these circumstances, and to check if any are more prone to suffer due to the imbalance with phenomena such as overfitting common labels. However, we do plan to explore the usefulness of such techniques in future work. Since the task concerns recognizing the genres across an entire song and not just segments of length compatible with the network inputs, we also include the post-processing step, which is applied only on the testing dataset. In particular, any MIDI file from the testing dataset is split into overlapping sequences, each of which is compatible with the input to the neural network. After feeding all of the sequences to the network, we then accumulate the resulting genre predictions by taking their average. We then assign as a predicted genre any which had a value greater than 0.5. If for a particular piece of music, no sequences have an average value greater than 0.5, then we assign a single predicted genre, the one with the highest average value at the output of the neural network. The evaluation metrics are then computed for each song and not for each individual sequence. So here we summarize all of our results. If I manage to change the slide. Okay, so here we summarize our results for all lengths, types of convolutional blocks, and types of inputs, which are either the original sequence or the sequence at multiple resolutions, annotated as MuSeReNet in the table and for both datasets. In general, using multiple sequence resolutions led to better performance for shorter sequence lengths when compared to longer ones, while for longer sequence lengths, using just the original sequence outperformed our proposed architecture. Furthermore, increasing the length of input sequences, which consequently increases the depth and total number of parameters of each network configuration, consistently improves performance up to a sequence length of 1024 time steps, which corresponds to 20 bars, about 20 bars at the 4/4 time signature. Performance seems to stabilize or even drop for the longest sequence lengths of 2048 time steps. We found it interesting that the shallow variations of the network configurations consistently outperformed the deep ones, even though they have the same number of trainable parameters. Finally, many of the configurations surpassed the, to our knowledge, state of the art, with the best performing configurations being significantly better. Okay, so here we show more detailed results on the test set of the topMAGD dataset for the best performing network from our experiments, which is the shallow sequence network with an input length of 1024 time steps. At first glance, the negative effect of class imbalance is apparent, since performance for genres with high support is significantly better than those with low support, as one can see by comparing, for instance, the metrics for pop rock versus those for blues. However, even for genres with low support, performance was acceptable in many cases, and the tendency was for higher values of precision when compared to those of recall. Finally, there seem to be some genres which are harder to predict than others from their symbolic representations. A good example of this is rap music, for which the network configuration achieved the worst performance. Our intuition for this is that the identifying factor of rap music are the vocals, which are non-existent in symbolic representation. And looking just at the underlying musics, which is represented symbolically, it is easy to confuse rap music with other genres, even for a human expert. So, to conclude, we have shown that one-dimensional convolutional neural networks are suited for the task of genre recognition from symbolic music. We got some interesting results with respect to the allocation of network resources, especially when comparing deep versus shallow networks with the same number of trainable parameters. These results motivate us to further explore this approach and merit further evaluation and experiments. In addition, we got some interesting results regarding the use of multiple sequence resolutions of the initial piano roll, which in some cases improved performance and in other cases hindered it. Finally, regarding the input sequence length, the logarithm of which determines the depth of the network with respect to convolutional blocks, there seemed to be an optimal configuration, which for us was at 1024 time steps. However, this also merits further experiments and evaluation in order to determine the significance of these discrepancies in performance. So we have many ideas for continuing this work and further exploring the use of 1D CNNs for symbolic music classification. Techniques for network architecture search, which are emerging as an important facet of deep learning, will provide us with a more methodical way of determining the optimal configuration of a neural network for the task, and of efficiently allocating resources, such as the number of trainable parameters. We are also exploring ways to utilize more meaningful tree representations of music, which exist in the literature, besides multiple sequence resolutions, in addition to more elaborate techniques for making use of the tree structure within the network architecture, besides treating each level of the tree as a different input. Finally, there is more information available which could be useful for solving the task, such as relationships between genres themselves, for instance, subgenres, fusions of genres, etc. Another piece of important information which is immediately available in many cases in the MIDI file representation concerns the metadata, such as, for example, the instrumentation of a piece of music, which for some genres of music is a very distinctive feature and can aid in classification. Okay, so thank you all for listening to our presentation, and I apologize for the technical difficulties that we had. There is more detailed information about all configurations, the training procedure, and the results in the full text of our paper and in the GitHub repository. And we are happy to answer any questions.
Thank you, Edmund. Please do the questions through chat or directly. Okay, I have one. Okay, the datasets include sets very unbalanced. Did you do any tests with okay, less sets but more balanced in order to see if that changes anything?
Yes, we did some small tests. We didn't do extensive experiments on this, and there seems to be an improvement when the balancing is done. However, we wanted the extensive evaluation to not include these procedures because in many cases in the wild, where such a model might be used, we might not have a good, a clear vision of a clear picture of how the genres are distributed. And this is also something that might change over time, for example, in a large collection of music. The differences in results were not very significant for the very small experiments which we ran. However, in the future, we plan to systematically test such techniques for handling the imbalance of the dataset.